We are going to work on matter today. We're talking about some different ways to classify matter. So we're talking about the two different types of matter, or two different ways to classify matter, are whether they are a substance or a mixture. Substances cannot be physically separated. They are going to have a homogeneous composition, meaning the same throughout, going to look the same, appear the same. Mixtures can be physically separated, and they will keep properties of individual substances. So two different types of matter that we're talking about. Now, we realize that matter can have many different characteristics. We can classify matter many different ways, but these are the two ways we're classifying them today. We can further divide substances into elements and compounds. Elements are the building blocks for all matter. They cannot be broken down by ordinary chemical means. Yes, you can split atoms using nuclear means, but we are talking about in a chemical reaction, you cannot break elements down. They're the building blocks for all matter. Compounds, on the other hand, are chemically combined elements. They usually do not retain the properties of the individual elements. Let me say that again. They do not retain the properties of the individual elements. So unlike a mixture, compounds do not retain the properties of the individual elements. So if you're taking 106 lab, you're going to do a demonstration. You're going to see a demonstration where you have a mixture of iron and sulfur in a test tube, and you can pull the iron out of the mixture with a magnet because it's just a mixture, because the iron is still magnetic. Yet when you heat the iron and sulfur up and make a compound that is iron 2 sulfide, then you cannot use the magnet to separate out the iron because it's a new substance. That's a new substance. It's a compound now. And the two properties of the sulfur being yellow and the iron being magnetic are not retained. Those two properties are not retained because it is now a compound. We use the term substance incorrectly many times. If we see something spilled, we may say, what is that substance? Most of the time what we see is actually a mixture, not a substance. The only two things that can be called substances in chemistry are elements and compounds. Now let's go to mixtures. So mixtures can be physically separated. We're going to talk in a few minutes about ways to physically separate mixtures, but let's look at the two different types of mixtures. We've got homogeneous and heterogeneous. Homogeneous means that they are the same throughout. That means that they have the same phase or same state, meaning it's all solid, all liquid, all gas. Sometimes these are also called solutions. If it's a liquid or gas, it's often called a solution. So homogeneous means it's the same throughout. Some examples of homogeneous would be sweet tea, where all of the sugar is dissolved. Coffee, black coffee, or coffee with sugar only would be a homogeneous mixture, and it's going to be the same throughout. Kool-Aid, all these are different examples of homogeneous mixtures. A heterogeneous mixture is one that is different throughout. Now, what makes it different could be that it is more than one phase, maybe more than one phase. State or phase means the same thing. Or it could just mean it's still all the same phase, it's just totally different things making up the mixture. So some examples of that might be trail mix, Raisin Bran, chocolate chip cookies, ice water. Those are all examples of a heterogeneous mixture. So when you're thinking about matter and you see something or are told about something, think about how you would classify it. Is it a mixture? Is it a substance? The only things that can be substances are elements or compounds. Is it a homogeneous mixture or heterogeneous mixture? Let's just take one for example, sucrose. Sucrose is white table sugar. What is that? Well, it's a compound. But what if I say sugar water? Well, that's a mixture. What kind of mixture? That's a homogeneous mixture because it's the same throughout. Now then, let's look at how to separate mixtures. What are our means of physically separating mixtures? Before we do that, though, let's quickly mention the word alloys. Alloys are a special type of mixture, and they are a mixture of metals. Specifically, they are homogeneous mixtures of metals. So they're a homogeneous mixture of metals, and they are examples, you've heard of these before, I'm hopeful: brass, bronze, stainless steel. Where are these alloys used? Alloys are used in jewelry. You've seen, in fact, almost all your jewelry is going to be made out of an alloy. Also, tire rims, airplane parts, artificial joints, lots of things use alloys because they have properties that are able to be retained from both elements that are making up that mixture. And so, for example, like your gold jewelry is some gold, some probably even some tin, just different elements that they're using to get the properties to make it strong enough and sturdy enough to be a gold ring, but still be as much gold as possible. If you made it out of pure gold, it would be too soft and it would actually not retain its shape as well as we would like for our jewelry to do. So those are some other special mixtures. So I wanted to mention that before we talk about how to separate mixtures. So we've got several different ways to separate mixtures. We're going to talk about several of these. First one we want to talk about is distillation. Distillation is using heat to evaporate and condense. It is usually used for homogeneous mixtures. We typically use distillation for homogeneous mixtures. I can show you a distillation setup just to give you an idea of what I'm talking about here. You may have seen this, may have actually done this even in a high school chemistry class. So what you're looking at is a Bunsen burner heating up a solution, a homogeneous solution that's in a flask. These blue dots are indicating that there is a vapor coming off. Let's just make an assumption real quickly that this is salt water. So you have the salt water solution. It's a homogeneous solution. You're heating it up to the boiling point of water. That's the thermometer that you're seeing sticking in here. Heating it up to the boiling point of water. As it evaporates, it's then being collected in this condensing tube. This is a water jacket that you see. Condensing, and then this is your distillate. So in our scenario, if this were salt water, what's coming out as the distillate is actual pure 100% H2O, nothing in it. So this is pure distilled water. If you've heard of distilled water before, that's what would be in this container. Once we finished evaporating the water, what would be left would be salt. And so in this container would be the salt. If by chance this were made with tap water, meaning coming out of the faucet, then in this container would also be some sodium chloride, probably from the water. You would also have some calcium deposits. You may even have some iron. Anything else that was dissolved in the water would be in this container as well. But this is for a homogeneous mixture. Now, you've also heard of distilling when it comes to alcohol or liquor. So what is that process? Well, in that scenario, this would be a mixture of ethanol, which is the drinking alcohol, as well as water, probably sugar, probably some other things would be in this container as well. But you're looking mainly at a process of trying to get out the ethanol from the water mixture. And so in this scenario, you would not want to heat it to the boiling point of water. You would want to only heat it to the boiling point of the ethanol. Then it would be evaporated. The ethanol would be then collected in this distillate container, or it is the distillate, and this would be ethanol. In World War II, when they were, many people were actually making moonshine and running it through their still twice because they had a fuel ration and they did not get enough gasoline and that they needed more gasoline, and so they actually would make ethanol and run their automobiles on the ethanol because that was a way to get fuel, and they could do it because they were very good at distilling. Those old stills, you may not realize, or you may realize, you may think this is an odd setup, because what you may be more familiar with are those copper coils that you would see in pictures. And this would be also even a copper kettle, and they would be heating it up. It would then run through those copper coils. Many times this would be done near a spring. And the reasons this would be done near a spring or a creek would be because they could then immerse the copper coils in the spring water, and that would cool them, and also it gave them the source of water to make their alcohol and to make the liquor. And so that would be one of the reasons you would almost always find these old stills near a creek. And so that process, again, was distillation. In that situation, you were actually separating one liquid from another liquid. And so it's a little different than the scenario I talked about. But distillation is a process of using different temperatures to get out one substance from another substance by evaporation and condensation. And it is usually for homogeneous mixtures. Another is filtration. Filtration, you've probably all seen. It's going to be used for a heterogeneous mixture. It is basically going to be a filter paper, filter cloth. It could be anything from straining cottage cheese or straining maybe whole milk if you milk cows. It could be, you could use just a filter cloth to do that, a piece of cheesecloth if you've heard of that before. Or it could be anything that's a very fine filter, such as in your vacuum cleaner or in your HVAC system. By the way, if you haven't changed your filter in your air conditioner heater system, you might need to do that soon. Those should be changed regularly. Our air is not perfectly clean. We don't see the particles in our air, but if you change your filter, you're going to see that there are things in our air, and that filter is catching them. A sieve or a sifting is also similar to filtration. It is also a method of separating heterogeneous mixtures. So it's also for heterogeneous. I'm going to just put a few notes here. Your air filter, coffee filter, these are all situations where you're using filter paper. For the sieve or sifting, if you're familiar with the Western's Farm, their compost and their mulch is run through a sieve. It's like a screen that they sift out the big rocks and get hopefully behind just some finer mulch or compost. Depending upon what they're making at that time, they use a different size screen, and that's the sieve. That would be considered a sieve. Centrifugation is another method of separating mixtures. Centrifugation is fast spinning to cause settling. It's fast spinning that causes settling. It is also used for heterogeneous mixtures. Two scenarios where you will potentially experience the effects or may have seen the situation with heterogeneous mixtures being separated with centrifugation. Blood is centrifuged. If you ever give double red blood cells at a blood drive, they will run your blood through a centrifuge to pull out only the red blood cells, and then you get back your plasma. Semen is also another situation that is centrifuged. If you're familiar with artificial insemination techniques in livestock or in humans, then the semen is run through a centrifuge to get just the sperm and leave the seminal fluid. So that's another example of centrifugation in healthcare for sure. Magnetism is a very simple method of separating mixtures. Magnets will attract iron, but not other metals. And so iron-containing mixtures can be separated. Recycling is a situation where magnets are used to separate steel cans from aluminum cans. Chromatography is another method of separating mixtures. Chromatography has a stationary and a mobile phase. And is based on the attractiveness of each phase. There are lots of different methods using chromatography. One is gas chromatography. One of the more common ones that you may have actually done in elementary school or middle school, maybe high school, even just as a simple experiment, is the chromatography of magic markers on paper or coffee filters. You may have even done this on t-shirts. If you take a water-based marker and put a dot of, say, a green or black marker on a coffee filter, and it's a water-based marker, then you can add water to that. And the different colors that make up that marker will be separated based upon the attraction that those dyes have for the filter paper as well as for the water, and they move. Same thing has happened if you've ever had a piece of lined paper like this paper. This paper is a lined piece of paper, and this is a water-based ink. And if I drop water on this, you're going to start to see separation of this blue color on this paper, and that's chromatography. That's the process of chromatography. So chromatography is used for homogeneous mixtures. Selective solubility or solubility extraction is another very common and very used method of separating mixtures. And the way that works is it can be used for either homo or heterogeneous mixtures. And basically how that works is one item in the mixture, or more than one, will dissolve in a solvent and others will not. So for instance, if we have a situation where we had sand, sugar, and we wanted to separate those, what would we do? Well, place in water. If we placed the sand and the sugar mixture in water, what's going to happen? The sugar would dissolve. We could filter out the sand with filter paper, and then we could distill the sugar water. And so we have separated them. Now, did we have to use more than just selective solubility? Yes, we did. But the solubility extraction or selective solubilities is what started the process, and then we used other methods of separating the mixtures. The final one that I want to talk about is just simply temperature differences. It could be placed up there under distillation, but what I'm referring to is a little bit different. Temperature differences. And that's a strange way to say it. But basically what we're looking at with temperature differences is think about the boiling point, the freezing point. Think about those points for different substances. And one of the easiest ways to think about a mixture and how you could separate it with temperature differences is very, very simply with the example of a roast. You've cooked a roast in your oven. You have it for supper. Let's say it's a nice chuck roast. and you're tired, you don't want to put it in another container, you're just like, you know what, I'm ready to go to bed. So you, after you've let it cool down a little bit, you put that roast pan with the roast in it and all the juice in your refrigerator. The next day you get it out to heat it back up, and you open the lid, and on top is this hard layer. If it's a beef roast, it's a hard layer of fat. And what you have just done is you separated the mixture of juice and fat by a temperature difference, because the solidification, which is the freezing point of the beef fat, is what the temperature of the refrigerator is, or in that range. And so you reached a temperature that would solidify the fat, causing it to become separate from the juice, and then you can simply peel off the layer of fat, and what's left behind is the juice. Now, when you put that in the refrigerator the night before, you may not have even noticed that there was a difference in that liquid in the roast pan, but the next day you notice it, and that's because of a temperature difference. So when you have mixtures, think about, can I separate it by one of these means? And there's other methods as well, but this is a pretty good overview of different ways to separate mixtures. So again, mixtures can be physically separated, and these are some of the ways we can separate those mixtures. All right, before we leave on this topic, I want to mention one more thing about elements. And we've got lots to do later with elements and compounds, but there is one thing, and these again are all under substances, so I'm kind of shifting aside here. So if you want to take the whole paper, you're looking at the right-hand side, deals with mixtures, and then this is all mixtures. And then I'm shifting the substances. Now I'm going to just real quickly talk about a special type of element that's called a diatomic element. Diatomic elements are those elements that do not exist alone in nature. So diatomic elements, there are 7 diatomic elements, 7 elements that do not exist alone in nature. They are either in their diatomic state or in a compound. They cannot exist alone in nature. They are unstable alone. They cannot exist alone. Who are they? Well, I learned them, and I'm going to teach you with this acronym, Hofbrinkel. And that stands for hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. How are they written? H2, O2, F2, Br2, I2, N2, Cl2. And those are our 7 diatomic elements. If you will look on your periodic table, you actually will see that they make the shape of a 7 where they're located on the periodic table, and then over here you will see hydrogen. So they have the 7 diatomic elements. It will be nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So they make the shape of a 7 pointing to hydrogen, which is the 7th one. But keep in mind, when anytime we talk about these from this point forward, and if we talk about the elements hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine, realize that they are never just H, O, F, B, R, I, N, and Cl. Just realize that for future reference. So what this really means then is that these diatomic elements are actually molecules. They are actually molecules. And a molecule is 2 nonmetals bonded together, 2 or more nonmetals bonded. So these are the diatomic molecules: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine.